Right, in this video, we're going to talk about suggested homework problems from 9.4. Let's go ahead and get started. Um, Hopefully you've read the notes, been to class, and uh, maybe even watched the supplemental examples video for this section. That would be good before trying to do the homework here. So let's go ahead and get started with number one. We'll be talking about the direct comparison test and the limit comparison test in this section. Let's ask about the direct comparison test first. So you want to compare series AN and BN where both are positive and BN converges for N between 1 and 5 inclusive. AN is greater than BN, and for N greater than or equal to 6, AN is less than BN. Explain whether the direct comparison test can be used to compare the two series. So let's try and draw a graph here for the situation that we have AN is going towards 0 because this converges, and BN is also going to go towards 0. And let's see, AN was greater than BN until somewhere out here. This is AN, and this is BN. And we know that BN converges. So because BN converges and AN is less than BN for some, I'll call this capital N, or the next integer above that you can call capital N, then AN also has to converge. So yes, we can use the direct comparison test here. And let's go ahead and clear the canvas. Back to 100% here. And let's look at number 7. So let's use the direct comparison test to determine the convergence or divergence of the series. 7 says summation from n equals 1, no, n equals 2 to infinity of 1 over root n minus 1. And I would like to call this AN, summation of AN, and I'm going to call summation of BN n equals 2 to infinity of 1 over root n. And because I have made the denominator bigger, BN is smaller. So BN is smaller than AN for all n greater than or equal to 2. Since I started at 2, I just need to make the statement about what my restrictions are here. And summation of BN diverges by P series. It's going off to infinity. So since AN is bigger, it also has to go off to infinity. Therefore, summation of AN also diverges by the direct comparison test, which I'll abbreviate DCT. So that was number 7. Let's look at number 9. Number 9 says summation from n equals 2 to infinity, ln of n over n plus 1. I'll do the same thing that the book did here. And I'm going to make Bn equal to summation n equals 2 to infinity of 1 over n plus 1. I want to verify this with my calculator because I can't tell you that for sure that this is correct starting at 2. So all other things being held equal here, I want to see when ln of n is going to be greater than or equal to 1. So that's going to be when n is greater than or equal to e to the first. N needs to be greater than or equal to e being 2.7 something or other. I need to bump this up to 3 and bump this up to 3. So an is greater than or equal to bn for all n greater than or equal to 3. And then I need to test for convergence or divergence of Bn using the integral test. So f of x equals 1 over x plus 1 is positive for x greater than or equal to 3, continuous for x greater than or equal to 3. Let's prove that it's decreasing. So decreasing for x greater than or equal to 3. So it meets all 3 conditions. Set up the integral test. Integral from 3 to infinity of 1 over x plus 1 dx is equal to ln of the absolute value of x plus 1 from 3 to infinity will approach infinity minus ln of 4, which approaches positive infinity and diverges. So Bn being smaller than An and divergent means that since Bn is smaller than An for all n greater than or equal to 3, and Bn diverges An series also diverges by direct comparison test. We could compare it to other series other than this one. We typically like to try to compare to a geometric series or a P series when possible. So if I were trying to compare this to a P series, I might try to make some multiple of 1 over n to see if I could get this to always be smaller than ln of n over n plus 1. And with a big enough multiplier in the denominator, such as bringing this 1 up to a 2, and bringing that ln of n down to a 1, both would make it smaller. So I think that I could get away with using a Bn of 1 over 2n as well. And then saying that Bn is a divergent p-series and that we could not need to use the integral test here. So let me show you that right here. If I use ln of x over x plus 1, and I have a Bn here of, let's say, 1 over, oops, delete, 1 over 2x in the denominator. And then I want to zoom 6, and I want to see if zoom 0 here, second calc intersect of blue and red. Somewhere right around there, 2.0 something. So again, I would like this to be for n greater than or equal to 3, that Bn, which is my red function, is smaller than An, which is my blue function. And we know Bn is a divergent p-series, so An would also have to be divergent. So that's another way that you could do this. That's not the series that the textbook chose. I went with the one that they chose, so your work would most closely match what's in CalcChat. There's no problem with choosing the divergent p-series 1 over 2n there. Again, I did that by making the numerator smaller and the denominator larger, both forcing a smaller series for comparison, Bn, because I knew Bn was going to be divergent. If it was related to the harmonic series here, it would go off to infinity, and that would push An off to infinity. So because I knew this was going to be divergent, I needed it to be smaller. Let's go ahead and look at number 15. Says summation n equals 1 to infinity of sine squared n over n cubed. And so let's call this summation of an, and I'll call summation of bn equal to summation n equals 1 to infinity of sine has to stay between -1 and 1. So sine squared is going to have to stay between 0 and 1. Call this 1 over n cubed. And so Bn is always going to be larger than or equal to An here, because sine squared has to stay between 0 and 1. And this is a convergent p-series. Bn series converges by p-series. Therefore, series for An also converges by direct comparison test. All right, moving on to the limit comparison test. And the limit comparison test is going to tell me to find a comparison series that is basically of the same power, so that I can take the limit as n goes to infinity and see if that is going to be a positive answer? And if so, I always try and force it to be a positive one. Then AN and BN both do the same thing. They both converge or they both diverge. And I try and choose a series for BN that I know what it's going to do. Again, usually a geometric or P series, maybe some combination of the two. So 19 summation n equals 0 to infinity, 1 over root n squared plus 1. And this will be my AN, taking the most powerful thing from the numerator to make my series for BN. I'll take same values here. So 1 over, and then the square root of n squared is going to be n. I'm not allowed to make that 0, I'll make that 1. So I'll say that I'm only interested in this from 1 to infinity, really, because of the domain of Bn. But I'm going to take the limit as n goes to infinity. So really, this number down here doesn't much matter, of AN over BN will be equal to the limit as n goes to infinity, 1 over root n squared plus 1 over 1 over n is going to be equal to the limit as n goes to infinity of n over root n squared plus 1. And since I'm going to positive infinity, I'll pull out the square root of n squared is n. I don't need absolute value bars for that. And the n's will cancel, leaving me with a limit as n goes to infinity of 1 over root 1 plus 1 over n squared. This term is going to go to 0. End up with 1 over root 1 is 1 over 1 is 1. And since this is positive here, AN's series and BN's series both converge or both diverge. Then the BN series diverges by P series. It's the harmonic series, which is divergent. Therefore, the summation for AN also diverges by the limit comparison test. Let's go ahead and look at number 23. Says summation from n equals 1 to infinity, 1 over n root n squared plus 1. I'm going to call this summation for AN. Summation for BN is going to be equal to summation n equals 1 to infinity of 1 over n squared, this n, and then the square root of n squared is another n. So I'm going to be comparing it to 1 over n squared. Limit as n goes to infinity, AN over BN is equal to 1 over n root n squared plus 1 over 1 over n squared. And I need this limit symbol in front of this. Goes to infinity is equal to limit as n goes to infinity of n squared over n root n squared plus 1. And this is n over that. So this is the same thing as limit as n goes to infinity of root n squared over n squared plus 1 equals limit as n goes to infinity of 1 over 1 plus n to the negative second will be root 1 over 1 is equal to root 1, which is a 1. So because that's positive, that means that summation for AN and the summation for BN both converge or both diverge. And then BN converges by P series. So summation for AN also converges by the direct comparison test. Look now at number 27. So we're told to use each test for convergence at least once. 27 says n equals 1 to infinity of cube root of n over n, which is going to be summation n equals 1 to infinity of 1 over n to the 2/3. This is a divergent P series. P is equal to 2/3 is less than 1. Let's look at 31. Summation from n equals 1 to infinity, 2n over 3n minus 2. If I take the limit as n goes to infinity, 2n over 3n minus 2, I get 2/3, which is not equal to 0. So this diverges by the nth term test. And then let's look at 43. So determining convergence or divergence of the series 1 over 200 plus 1 over 400 plus 1 over 600 plus 1 over 800 is 1 over 200 times 1 plus 1/2 plus 1/3 plus 1/4 plus dot 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 is equal to 1 over 200 times 1d 1 over n equals 1 to infinity. So this is a divergent P series. The constant multiple doesn't matter. So this diverges. All right, that's it for this video. And we will come back next time and talk about suggested homework problems from 9.5, where we will talk about alternating series, and we'll talk about conditional convergence and absolute convergence. So see you for the next video.